I will start with an article in Heidegger, or you can call it Heraclitus 115, an article by James T. Cushing, or an excerpt coming from his Philosophical Concepts in Physics, the historical relation between philosophy and scientific theory, from Cambridge University Press of 1998, page 45, Greek edition. Introduction: The metaphysics in physics. The ontological question in modern physics found itself in the front line of interest in the first half of the 20th century, and seemed to be leaving it at the end of that century. Not because it stopped to be interesting, but because there is no way to deal with it. The question is, what is the nature of the world in which we live? What is the structure of the universe? The non-informed will assume that this question has an almost obvious, and I would say direct answer. But when we enter the world of the very small or very large objects, it remains essentially unanswered. However, the answer to the ontological question remains important for all those who have philosophical concerns, and also because the answers form the central lines that scientific research follows. Ontology is nothing but metaphysics, and modern science has been developed basically in conflict with the traditional theological metaphysics. This is probably the reason why metaphysics have approached the ontological problem of physics solely from a perspective of metaphysics, and underestimate or even ignore traditional metaphysics. As a result, approaches based on the territory of traditional metaphysics are not very popular. It's actually what we said before. The result is to focus on the development of mathematical formalism that is believed to describe the physical world, and build mathematical models that are increasingly complex and ever harder to control if they are truly related to the natural world. This path leads from one dead end to another. A typical example is string theory or quantum gravity, which attempt to answer the question of the fundamental structure of the universe, which have ultimately led to a swamp. This current situation may justify the investigation of an alternative road, the one of traditional metaphysics. In my doctoral thesis, I follow this underestimated way of thinking, which led me to the hypothesis of logical quanta, HLQ. The HLQ is a metaphysical proposal which aims to answer the interpretational problem of quantum mechanics through the framework of the theory of logi of beings, as it has been developed in ancient and medieval philosophical thought. This is mainly inspired by Roger Penrose's book, which is called The Road to Reality. And it is by Roger Penrose. The Road to Reality, Jonathan Cape, London, 2004. Not only because there you'll find all you need for this work, but also because it is given in a way that makes it suitable for a philosophical paper such as this. The ontological problem of modern physics and the theory of logi of beings. There are many ways to describe the ontological problem of modern physics, especially in quantum physics. There are also many natural phenomena which reveal it, in other words, in which it appears. The problem can be summarized as follows. the entities are microcosms, i.e. photons, electrons, etc., while in the interval between two successive measurements of one of the properties appear to have features that none of the entities known to us can have, e.g. they appear to exist throughout the entire space or time, they communicate with each other, spooky action at a distance, in quite paradoxical way, etc. On the other hand, the entities of macrocosmos show none of these characteristics, despite the fact that they are certainly formed by the entities of the microworld. Point taken. The problem then is typically philosophical. What is the nature of the fundamental constituents of our world? What is ultimately the nature of universe? These questions attract the interest of human mind from the beginning of philosophy. But the one known as quantum paradoxes maximized this interest and also highlights the importance of the correspondence in epistemological questions. This interest is directed primarily to entities and events that are not directly observable but are perceived from the result in various experimental devices or by certain natural phenomena which are felt directly by our senses. The former is most definitely Schrödinger's cat. E.g., the question what is the nature of gravity, which is an immediately noticeable effect, but the cause that produces it cannot be seen. While those involved with the philosophy of science recognize that all these modern questions were at first posed and studied by the Ionians and then natural philosophers, and were processed by ancient philosophical thought, a fact that was recognized by the pioneers of modern physics. The latter do not believe that the answers provided by the ancient philosophers could be useful today. It is likely that this is due, to a certain degree, to the fact that they know neither the whole nor the depth of ancient philosophical thought. So the ancient philosophical tradition, along with others, developed a description of the entities that constitute the entirety of human experience, which we today call the theory of the logi of beings. This ontology has been of particular interest, but has a huge communicational handicap. It was developed as part of the theological controversies of the Middle Ages, or rather was the canvas upon which the theological controversies of the Middle Ages were based. The main corpus was developed in pre-Christian era, but the full expression was acquired in the medieval times. As a result, it was known mainly in theological circles and remained essentially unknown to non-theological ones. And right here lays the importance of my doctoral thesis, in which I recorded the full development of the concept of logos as the ontological foundation of the natural world. I began from the text of the pre-Socratic philosophers, especially, of course, Heraclitus, and reached to the writings of Maximus the Confessor. This presentation also highlighted the possibility that are opened by philosophy of the theory of logi of being set up an interpretive scheme able to respond to the needs of the philosophy of science. So according to this model, we could say that the beings are complex. Their entirety is made from the logos or from what man experiences in his senses. The being is determined in all its physical characteristics and its relations with other beings by its logos. Or conversely, the logos is an entity over which the being is somehow sitting on. Logos and being are inextricably entangled to each other, and the action of the first affect the other. However, there is a very interesting difference. The beings live in time and space, but the logi live outside of time and space. Also, as logos may be pure logos, that is not being expressed in space and time. That is, a logos who has not entered into space and time. A very important feature of the theory of logi of beings is that the logi have a linear tree structure. Although each compound logos is a composition of different logi, it may have additional properties that the individual components do not have. These features of theory of the logi of beings make this scheme suitable for the development of ontology of the natural world as a model to explain all natural phenomena which pose unanswered questions to the traditional ontology of physics. 3. Logi space, or logi of beings and the space of phases. I begin by presenting my interpretation of my model by looking at a simple physical entity, a normal physical body. According to the theory of logi, the relationship of logos to the entity is continuous. The logos specifies the individuality of being, i.e., its characteristics, namely the mass, charge, spin, etc., and also determines the motion, i.e., its evolution in space and time, and its relations with other entities' bodies. Conclusion. We can represent this relationship of logi to entities as space, in which the logi live as the base upon which is established, i.e., ontologically founded the world of phenomena we observe. This space I call logical space, and the world of phenomena I call physical world. Each point or possible area of the logical space is continually associated with the corresponding entity in the physical world. In modern physics, there is a similar form, but reverse. Specifically, to consider a physical system, i.e., to describe and predict its evolution in space and time, we use the so-called space of phases, which has other names such as space of places or configuration space. I think we remember this. This is coming from chaos theory. Phase space is the true space, and this of course also has connections to the Klein bottle logic. The Klein bottle is a phase space in itself. This space is an abstract mathematical space that has as many dimensions as the independent variables or degrees of freedom that determines the system status. Each point corresponds to a complete description of the system status at a certain instant of time. The full description includes all elements and all the characteristics of these elements of the system. What is important and interesting in this description is that in the space of phases exist entities that may have a known structure which describes the evolution of the system completely. These entities are mathematical functions with relatively simpler form than the functions described in the system directly, but not only. The system can be completely incomprehensible in direct contact, but the function describes it in the spaces of phases may be quite simple or even have very specific properties. The space of faces is usually a vector space of many or infinite dimensions and often has specific characteristics, symmetries, that defines it and help us draw very important theoretical and practical conclusions. Even when we may not have a comprehensive approach of it. Now we come to the face space. Nice with a recapitulation. I think this is ages ago since we went through this. The face space is an information space. It provides us with information on the evolution of the system, i.e. information about the life of the being. This observation, combined with all the previous ones, leads us naturally to the correlation of face space and the space of logi of beings, the logical space. In fact, if one considers the theory of logi of beings, he will be led to a slight change in wording, like the following. A mathematical entity in space of faces does not describe a being, but she prescribes it. Therefore, she has an ontological content, has a kind of physical nature, and is a special type of physical entity. Let me explain that. In face space, physical features is one dimension in face space. It is not complete without other dimensions. The physical reality is good, but is not complete. That could be compared with the complementarity between a wave and a particle. Both are needed for daily life, but they don't combine. We need both of them in a complementarity. The system and the face space are inseparable. A being is formed by the space of faces and its implementation expression of the physical world. The space face is another side aspect of the physical world and mathematically can have infinite number of dimensions and is equivalent to the logical value to which I referred earlier. So, a being is extended both in logical space and in the physical world. And the fundamental reality is not the physical world, but in logical space. What we perceive as physical reality is consequential. You can call it sort of derived. Totally different to that which our common intuitions inform us. And this is very close to what Age Bohr said to the students or doctorates. Do not come with entities. Do not come with existences. Come with that which is more important, more pertinent, more encompassing. Come with the things that are from the whole, not what is conclusive, indirect, derived. Because the physical world, and this is very interesting, according to quantum mechanics, what we usually call the physical world does not have enough information. It's not sufficient for us to live in. We need quantum mechanics to live in it. And this is something suggested among other people by James J. Gibson. When we try to live in Newtonian world, we will clash with the bigger hollows. What is the totality of everything? And the author of this article, James T. Cushing, he means that the logical space, what he calls the logical space, what I will call face space, is more fundamental. And the physical reality is a derived thing. Very close to the Penrose example. It's not a coincidence that he mentions Roger Penrose. The tennis game is the real thing, the real McCoy. When Federer plays his tennis ball, that's reality. When you're sitting on the lectern and observe and call that physical reality, that is secondary, it is derived, it is not of reality directly. It's more like a sort of an explanation. The real experience can only be had by Roger Federer. The other ones don't have that, they have existences only. And that's not enough for quantum mechanics. Neither is it comprehensible or sufficient for us to understand the world as a whole. It's a very interesting clarification that lies in this paper, although it's a rather complex. The logical space is not exhausted at the faces of space. The face of spaces is a mathematical construction that is limited by the capabilities of mathematics that have been developed so far. So far is important. It will develop further, but it will be no end to that development. We will never fully be able to depict, not even in mathematics, phase space. It will never happen. It can go further, but it will never happen. The logical space as a physical reality is broader than every description that can be built by man, same as happens generally about the physical universe. Here are posed all the epistemological questions raised by the philosophy of science. What is important is to note that the space of phases we reveal as such because there exists the logical space, because the universe is built on the logical sense or the logical space. This is another way of showing why contradictions are important, because the logical space goes beyond the contradictions, it's greater than the contradictions. Contradictions is what we see in the physical world, or think we see. That could also be questioned to a certain degree, not completely, but to a certain degree. In this sense, we can assume that mathematical entities that exist in phase space correspond to the logi, but there must be more logi which we cannot describe with a function. To understand the structure and properties of the logical space, we can use the knowledge to be gained from the study of the logi, who we can study mathematically. When we construct a model for the natural world, we should make a generalization of the conclusions to be drawn from this study. Under these circumstances, the generalization will be neither arbitrary nor unreasonable. Four, the formation of the logical space. The aim is to develop a model that can represent the entirety of the physical reality, i.e., both the physical reality and the logical space. For the purpose we use the mathematical tools available to us. Here is posed strongly the question of the relationship of our model with physical reality. This question, found in all scientific fields, has no definite answer. I will make some assumption on which I will follow. First is that the physical world actually exists, very important, and as we perceive with our senses. Second is that we cannot understand the fullness of the natural world only with our senses. So we expand our knowledge by logical thinking, philosophical thinking. 3, we still do not exhaust the physical reality. There is always something we miss. I would say this is exactly as Heraclitus. The human senses have direct access to the four dimensions of space-time. The existence of the logical space compels us to add extra dimensions, the ones of the logical space. For the mathematical description of such cases has been developed the mathematical theory of fiber bundles, which is appropriate to describe what we are looking for. The fiber bundles are used to describe physical realities and the corresponding physical models with more than four dimensions, something that is very common in modern physics. Let us now describe how our model works. In ontological terms is first and foremost the logical space in which logi live. The logi can be considered as compounds of instructions and information. The logi have the capacity to express themselves in physical space and thus to maintain the existence of beings, those which we observe in the natural world. All these physical realities described mathematically by a set of fiber bundle, in which one can be considered as a base to every point lambda of L corresponds to the fiber me. The set of me expresses and describes the physical world. The point lambda moves in a way that we will describe later. The curve on which lambda are moving corresponds to the physical space to the points of intersection of lambda to me through a process of elevation of the base of the total space, a process that is reversing the normal projection. So what we've gone through here is phase space show that everything we experience is real, but it's in a way that we usually cannot fathom. It's not all. If we conclude that what we see or experience is all, we will be at miss. This mathematical theory proves that. So it's a mathematical equivalence to the quantum theory. Start with what we consider to be real. Start with what happens at the lectern in Wimbledon when looking at Roger Federer. You will be lost. You will not have the totality, and you will be stuck in a certain dimension or angle of the phase space. And by proclaiming that this is the reality, you will end up with a diminution of reality itself. You will not have access to it all. So what he goes into can be said to be a sort of mathematical Heraclitean vision, a way of showing if we get stuck in the Milesian concept of the physikos, we will be at loss. And if we start that as a reductionist manner, if we say this is fundamental and we are going to build the whole world from that, like an arche, like Democritus, or for that reason, why not Albert Einstein or Newton, we will lose everything. We will go to something that is derived. And if we from that one construct a whole worldview, we will be even further separated or removed from reality. And I thought this article was especially interesting since I didn't know it was mathematically proven that physical reality is not enough, but it is. And of course, that mathematical proof is also included in Julian Barber. Julian Barber also showed, by starting with the idea that there are physical entities in empty space, definable by X, Y, Z, we will not be able to understand the world, not even the physical world. And this can, of course, I am now, spoiler alert, for the ones who will be able to watch this and see this before the lecture I will be giving tonight in quantum mechanics. This is the same as Gödel's mistake. The idea that you can derive mathematics from the experience mathematics, what we perceive to be the mathematical entities, that will not be possible. Actually, we will cripple mathematics. That will no longer be mathematics, since even mathematics itself is coming from something that is greater. And I hope you can understand the parallelism here with Heraclitus, because Heraclitus says if you get stuck with one part of the opposition, for instance, which is most common today, existence, not only will you be giving up non-existence, you will also completely lose existence, because you cannot derive existence from existence. Exactly in the same manner as you cannot derive mathematics from the axioms coming from mathematics. To do that is lethal. It's a self-sacrifice. It is literally the suicide of Gödel himself, who starved himself to death. Not unimportant in this revelation, so to speak. And now I think it gets much clearer why contradictions are so important and how they point to something that is more, so to speak, fundamental or founding, or from a place where both contradictions comes. And if it's let to be hidden, if it could be in the shadow, if it can be in the seam in between alatea, thea, or dorsal or ventral, it can do its work. But if we try to make it ontic, if we try to capture it by existence, then we strangle it. And we will be at lost, exactly as Gödel, Hilbert, and actually I have to add another 40-50 mathematicians in the 2030s. All of them succumbed. There was a whole generation of mathematicians that either went into depressions, schizophrenia, or actual suicide. It is a conundrum that Heraclitus tried to steer away from by using the Milesians. I stated that many times before. Without having the idea of existence, it's very hard to show that contradictions are important to understand the greater whole. So he needed the Milesians. He's not criticizing them, as many interpreters are saying. They are absolutely necessary. But he also tries to stir us away from a possible trap, an endless cave or endless hole to fall into, a black hole. And if that black hole captures us, for me it's very hard to see any return. Very, very hard to get out of that hole, because every try you make will actually, I put a pause here. Every try you make to get out of the hole will do the same mistake as the Northern School we mentioned earlier. It will make the liberation or the wholeness an entity, an object that will diminish the whole thing and from the very outset make it smaller. That is why prajna is absolutely necessary. And I would say it's combination with the Northern School of Discipline, which I think we have been doing the last 1100 lectures, but with the adding of prajna. Prajna is the magic elixir or the slap of the face, a sort of direct happening that can sort of in an instant move us from the toxicity of the whole, of the staticness. And where every trial that we make to get out of the hole is like walking in quicksand. What happens in quicksand? For every step we take, we make the quicksand stronger. And it's a horrible view to see. You can see on YouTube how people are striving to get out of quicksand. The more you try, the further down you go. And this is actually the destiny of every single philosopher, except Heraclitus, and possibly with the exception of Heidegger and Wittgenstein. But all others have stranded in depression, given up, like for instance Quine, being pre-early dimensioned, like Searle, and so forth and so forth. It is a disaster on a personal level, and it's a disaster on the global level. I will continue with something else, so I'm at it. This is an article by Lisa Ziga, who looks at this problem from yet another perspective. I see, as many perspectives as we can put up, the better it is. Space-time may have fractal properties on a quantum scale, by Lisa Ziga, published in Physics Organization. As scale decreases, the number of dimensions of K-Minkowski spacetime, which is an example of space with quantum group symmetry, decreases from 4 to 3. In contrast, classical Minkowski spacetime is 4-dimensional on all scales. So you see, if you put the scale small enough, all of a sudden one dimension will disappear. This finding suggests that quantum groups are valid candidates for the description of a quantum spacetime, and may have connections with the theory of quantum gravity. Well, as if extra dimensions weren't strange enough, new research has proved that an even more mind-bending possibility, and that is that space-time has dimensions that can change depending on the scale. And the dimensions could have fractal properties on small scales. In a recent study, Dario Benedetti, a physicist at the Perimeter Institute at Waterloo, Ontario, has investigated 2 possible examples of space-time with scale-dependent dimensions, deviating from classical values at short scales. More than being just an interesting idea, this phenomenon might provide insight into quantum theory of relativity, which also has been suggested to have scale-dependent dimensions. Benedetti's study is published in a recent issue of Physical Review Letters. Quote from there: "It is an old idea in quantum gravity that at short scales, space-time might appear foamy, fuzzy, fractal, or similar. In my work, I suggest that quantum groups are a valid candidate for the description of such quantum spacetime. Furthermore, computing the spectral dimension, I provide for the first time a link between quantum groups / non-commutative geometries and apparently unrelated approaches to quantum gravity, such as causal dynamical triangulations and exact renormalization groups. And establishing links between different topics is often one of the best ways we have to understand such topics." End of quote. In his study, he explains that space-time with quantum group symmetry has in general a scale-dependent dimension. Unlike classical groups which act on commutative spaces, quantum groups act on non-commutative spaces. That is, where xy is not the same thing as yx. Very strange. Which emerges through their unique curvature and quantum uncertainty. Here Benedetti considers two types of space-time with quantum group symmetry, a quantum sphere and a K-Minkowski spacetime, and calculates their dimensions. In both spaces, the dimensions have fractal properties at small scales and only reach classical values at large scale. In simple words, he says, the relation between quantum groups and non-commutative geometry is as follows. Classically, we know that certain spaces are invariant under the action of some classical groups. For example, Euclidean space is invariant under rotations and translations. A quantum group is a deformation of a given classical group and is such that no classical space can have it as a symmetry group. The invariant space has to be as well as a deformation of classical space. A deformation that makes it non-commutative. No relation of all these two fractals is known, but in my work I found that they do have a common property. That is a non-integer dimension at some scale. This is quite extraordinary. We always assume in classical physics, in mathematics, in geometry, and I would say even our friend, which we met yesterday, no mentioning any name, would say that dimensions are scale independent. It's not hard to see why it should be that way. Otherwise, how could you put in a small particle into the grid of dimensions? Because the dimensions are the independent space in which you locate things. In this, something of the absolute most important for classical physics and Einsteinian physics as well. That is of the dimensions being completely unrelated to scale is being put into question. This is quantum space at its worst. I think this would be enough to put a classical physicist into a mental institution. It's grave. And actually this is the first time I hear it as well. I was just intrigued by the fractal dimension of quantum groups. Compared to a Euclidean sphere, a quantum sphere curvature and uncertainty make it a non-commutative space. When calculating the spectral dimension of quantum sphere, Benedetti found that it closely resembles a standard sphere on the larger scale. However, as the scale decreases, the dimensions of the quantum sphere deviates and go down to zero. He describes this phenomenon as a signature of the fuzziness or uncertainty of the quantum sphere, and also as a resulting from fractal behavior at small scales. In a second kind of space, K-Minkowski spacetime, the dimensions also deviated from the constant behavior of classical Minkowski spacetime. While the latter always has 4 dimensions independent of scale, the number of dimensions in the quantum version decreases to 3 as a function of the scale. In both K-Minkowski spacetime and quantum sphere, the dimensionality becomes non-integral. That is, it doesn't follow the sequence 1, 2, 3, 4, 5. Instead, you have dimensions in between 1 and 2, and 2 and 3, and 3 and 4. And this is typical and a signature of fractal geometry. Benedetti's results match previous approaches to quantum gravity, which also point to the emergence of a ground scale spacetime with fractal properties. Together, these studies may help scientists understand the unique Planck scale properties of spacetime and possibly tie it to a quantum theory of gravity. For instance, as Benedetti explains, the fractal nature of quantum spacetime might enable gravity to cure its own ultraviolet behavior by dimensional reduction. The main problem with gravity is that apparently it cannot be quantized as other field theories. In jargon, it is said to be non-renormalizable. The problem is specific to 4-dimensional spacetime. If spacetime had only 2 dimensions, the quantum gravity would be much simpler and treatable. The problem with a 2-dimensional theory is that it is unphysical, as we see 4 dimensions at our scales. Things can be solved combining 4 and 2 dimensions at different scales. That is, if gravity itself provides a mechanism by which the dimension of spacetime depends on scales at which we probe it, 4 at our and larger scales and 2 at very short scales, then we could have a physical theory compatible with observation that is free of quantum, that is, short-scale troubles. If you take a look at the structures that form in universe, many of things we see on large scales appear at smaller scales too. The dark matter halos that form around the largest bound structures we know of appear identical to the ones that form around Milky Way-sized galaxies. And intergalactic space itself. On the largest scales in the universe, gravitation is the only force that matters. Under many circumstances, if you wait long enough, gravitational collapse will produce identical structures, just scaled up and down in size depending on the size of your system. The idea that if you zoom in far enough, you'll eventually encounter a structure that repeats the initial patterns you saw on larger scales is mathematically realized in the concept of a fractal, when similar patterns repeatedly emerge at smaller scales and smaller scales. We can analyze them mathematically and see if they have the same statistical characteristics as the larger structures. If they do, it's fractal-like in nature. So is the universe itself a fractal? The answer appears to be almost, but not quite. Here's the science behind why. Mathematically, most of us are used to real numbers. Real numbers are like 1, 2, 3, 4, 5, 6, 7. Numbers that can be expressed in decimal format, even if that decimal is infinitely long and even if it never repeats, like pi. But there are more numbers that mathematically exist than just the real ones. For example, there are complex numbers. complex numbers have a real part, but also an imaginary part, which is a real number multiplied by I, something we discussed yesterday and gave me a headache, which is defined as the square root of -1. They include the real numbers, but take us beyond the limitations of working with the real numbers alone. The most famous fractal is the Mandelbrot set, which is illustrated in the complex plane where the x-axis is real and the y-axis is imaginary. So we have an x like this, whereas the y is imaginary. The way the Mandelbrot set works is to be represented by the border between what is actually in the set versus what is outside it. And this is very interesting. A Mandelbrot set can be visualized both with what it contains and also by which it's the things that it doesn't contain it. So the Mandelbrot set that looks vaguely like this. This is a Mandelbrot set. It depicts at the very same time both what is outside of it and what is inside of it, endogenous and exogenous at the very same time. Something that regular mathematics finds completely impossible. But that is actually what the Mandelbrot set does. When you see a small region that has truly identical properties to the entire set itself, we call those regions self-similar. That is also what is called iteration. If something has almost the same properties as the largest set, but with subtle differences, it exhibits quasi-self-similarity. But if the small region has truly identical properties to a larger region, then it exhibits true self-similarity. In the Mandelbrot set, you can identify many regions that show both quasi-self-similarity, which is more common, and true self-similarity, which is less common but still exists. We mathematically demonstrated this on scales spanning hundreds of orders of magnitude, which is far larger than the physical scales that take us from the smallest subatomic distances to the entire observable universe. And I can imagine that it goes even further than that. And here we can see regions are both quasi-similarity and exact similarity. Exact similarity you have at the bottom here. And that goes to show that the Mandelbrot set, which encompasses in a way the whole of universe, because when we speak about the entire observable universe, we can say the whole of universe, because it's a set, it's a thing, which is at the same time not the thing, because it encompasses both all that which is within it and all that which is without it. And it's not hard to understand that from a regular perspective, from my layman perspective, or even as an engineer, that doesn't make any sense. But this once more points to the wholeness that is before existence and non-existence. The wholeness that is before the division between inside and outside. The before of the small and the big. It is in a way larger than those things. And it also shows that exact similarity, identity, also comes from something that is not identical. And I would say, yeah, that's a good idea. Let me help you here. Take them that side. I'm following the sun here. So instead, as is usual in normal mathematics or in normal physics, where we start with what is identical and then we work our way up to a larger scale. Here we see that self-identity, something that is originally self and a genuine individual or atom, does come from the wholeness, not from the reductive sense. And I would say this in a way also resembles the division we have nowadays between ratio / logos and myth. Because if this sort of encompasses everything, the set in itself is a proclamation, it's a proposition. It's a proposition that has a truth value. What sort of truth value does the Mandelbrot set have according to normal people? It will have the truth value of F and T. Will be both false and true. Why is that? Well, because it encompasses the totality of universe. Then it has to be false and true. Because there is no single sets in normal mathematics or classical physics or any statement made by any man that is not either true or false. This is Heraclitean indeed, from fractality now. If we take the whole word, some statements has to be false. Otherwise, all is wrong. And that means that the division between mythos and logos is not as clear-cut as we usually think. And oddly enough, self-similarity or identity, which is very important for us to preserve, doesn't come from struggling to keep existence, an existing soul, an existing intention, an existing up. It comes from taking in the whole. And it's the whole, because it's scale independent, which preserves the little. And this actually goes back to something that we discussed once more yesterday, dark matter. In the late 20th century, it's quoted here, the universe as a whole appears to have a large amount of unseen, invisible mass to it, what we know today as dark matter. 2. The overall spatial curvature of the universe is consistent with being flat, meaning that if you add up all the forms of energy present in the universe, they equal the critical density determining the expansion rate, among other things. And that is, in physics, astrophysics, cosmology, we can know adequately, and we cannot adequately simulate the entire universe to arbitrary precision. What we can do instead is make some simplifying assumptions and then simulate the universe to the best of our abilities under that very set of assumptions. One of the more interesting things that we started to do was to run simulations of dark matter in the universe on a variety of scales. Perhaps surprisingly, they all yielded practically identical results. When you start with a universe uniformly full of dark matter, the same gravitational physics is always at play. no matter how uniform you make it, there will always be tiny imperfections, an atom or a molecule that isn't perfectly distributed, a tiny attractive or repulsive force on a subatomic particle, quantum jitter, etc. As soon as your system isn't perfectly uniform any longer, and the perfect uniformity is unstable under the laws of gravity, the overdense regions are going to preferentially attract more matter than the surrounding regions, while the underdense regions are preferentially going to give the matter up to the surrounding regions. If you start with just a single overdense clump, like a planet, and you allow it to evolve for long enough, you're going to get a large dark matter halo, spheroidal, diffuse, and with its highest density in the center. What's remarkable is that even if you widely vary your assumptions, you almost always get the same density profile, getting denser at a specific rate until a certain turnover radius, then getting denser at a slower rate until you reach the center. And this is what we could call the Einstein-de Sitter universe, where the only thing making up the universe is matter, and we have enough matter to reach the critical density where the amount of stuff exactly balances the initial expansion rate. In this toy model of the universe, the infinite range gravitational force propagates outward at the speed of light, which is equal to the speed of gravity, and there is no limit to how large or small a scale can get. You still form the same structures. But our universe fundamentally differs from this scenario in three important ways. Number one, we don't just have one type of matter, but we have two, normal and dark matter. While dark matter behaves in this self-similar fashion, normal matter is limited. It collides, forms bound structures, heats up, and even triggers nuclear fusion. Once you reach the small scales on which this occurs, self-similarity ends. The feedback interactions between the normal matter and the dark matter will alter the density profiles of the halos in ways that are not easy to figure out. In fact, this remains an open area of study in dark matter research today. The second is, matter is joined by radiation, an incredibly important component of the universe. Radiation, because it has an energy that depends on its wavelength, was actually more important in the early universe. When the universe expands, it gets less dense. The number of particles, normal matters, dark matters, and photons remains the same, while volume increases. But as the universe expands, the wavelength of radiation in it also redshifts, becoming lower in energy. The radiation was more important early on and gets less important as time goes on. This means for the first few 100,000 years of the universe, and especially in the first 10,000 or so, the matter over density struggles to grow as the radiation works too effectively to wash them out. There's a lower limit to the scales at which the universe is self-similar even at early times. Your smallest scale structures are going to have at least 100,000 solar masses in them, which is approximately the masses of globular clusters and the smallest known dwarf galaxies. Below that, the only structures you get are formed from messy collisions and interactions between various normal matter-based structures. Number 3. Our universe is also made extensively of dark energy, which dominates the energy content of the universe today. If the universe kept expanding while gravitating, and if the expansion itself wasn't accelerating, there would be no upper limit to how large these cosmically self-similar structures could be. But because dark energy exists, it basically sets up an upper limit to the size of the structures in this universe. Roughly a few billion light years across. That might sound enormous, but in an observable universe that extends for 46 billion light years in all directions, even a structure that was 10 billion light years in all 3 dimensions, a value much larger than the largest known structure in the universe, by the way, would occupy only 1% of the volume of the universe. We simply don't have structures that large and never will. So when you take all of this together, it helps us realize a true but perhaps counterintuitive fact about the universe. On both the smallest and largest cosmic scales, the universe is not fractal-like at all, and that only the intermediate scales have any chance of exhibiting fractal-like behavior. Still, this is itself a rich field of study. People have been working to measure the fractal dimension of the universe for more than 3 decades now, attempting to decipher whether it can be well described by one simple fractal parameter or whether multiple ones are required. The nearby universe is no good place to measure this, as dark energy has already reared its head for the past 6 billion years. But if you look at objects that are at redshift of less than 2 or greater, we are looking back in time to an era where dark energy was insignificant, the perfect laboratory for studying just what type of self-similar properties the universe had. With a new generation of ground-based and space-based observatories coming online over the next few years, we finally get the comparison between theory and observation that we always wanted. The universe isn't a true fractal, but even in the realms where it is only approximately a fractal, there are still some compelling cosmic lessons just waiting to be learned. Here, a very important factor comes in from chaos theory. This is facts coming from Stanford University and Lawrence Livermore Lab. And they made computation of the following. And the best way to describe that is to take a personal history. Listen to this story about Ming Guangwan's work on controlling chaos. For him, the natural world of phenomena would be too unpredictable to face head-on. All those unleashed floods of passionate color bleeding extravagantly across the sky. As we talked, it occurred to me that, of course, such a man would find his happiness in mathematical order. Unable to contain his own emotions, he would strive and flourish in the world of theory. Minh Dong Wan was born in a village in Vietnam sometime around 1940. He doesn't know his birthday. His father worked as a janitor at a Jesuit school. Ska vi gå till Shamsi?
No, not yet.
His father worked as a janitor at the Jesuit school, and when he couldn't work one day, Minh took his place. The Jesuit befriended the boy, who had a knack for math, and sent him to France to be educated. He returned to Vietnam briefly, then found his way to Cornell, then Stanford, and then to Lawrence Livermore Lab. He was among the first Vietnamese to receive a PhD in the United States. His academic specialty is case theory, specifically controlling chaos. In fact, his reputation rests with his experiments in controlling chaos in laser. For the last few years, however, he has been applying his ideas to heart defibrillation. The science of chaos began in the 70s in Santa Cruz, California, and quickly spread through the scientific community. Today there are around 20,000 practitioners. It is a branch of physics that concerns itself generally with disorder in systems, with fluctuations, irregularities, and anomalies. It is concerned with observing patterns, periodicities, and non-linear equations. Many people are familiar with the startling shapes and patterns of fractals, the non-linear geometric images of chaos and of order. As James Gleick says in his popular book on the subject, Chaos, Making of a New Science, where chaos begins, classical science stops. Anyone who has ever approached the Tibetan practice of samatha meditation will be familiar with the idea of controlling chaos, remembering metaphors that various teachers had used for the mind in its everyday state: turbulent, out of control, chaotic. I told Minh that controlling chaos sounded like a title for a weekend meditation intensive at Esalen. It should be, he said. I thought of other Buddhist description of the world, and Minh, as he sat next to me in the dark that night, talked of chaos. Central to both chaos theory and Buddhism is the practice of working from the inside out, of beginning with the projector, not the projected. Both in Buddhism and chaos theory, the material at hand is used for transformation. Fierce deities are employed to dispel negativity, or irregular signals to the heart are used to cure irregular heartbeats, defibrillation. Both disciplines view system as open and susceptible to change at any point. Both are about process rather than object. Chaos theory is referred to as a science of process, and Buddhist meditation as a practice. Note the similarity with the Mandelbrot set, where both inside of the Mandelbrot set and the outside is included in the mathematical description. Compare this to open systems. We usually regard ourselves as a closed system. We disregard what is behind us. We don't care what is in front of us. We shrivel, we became smaller, and we do not ground ourselves in terra, and we do not open up to the openness of the sky. Those things are caused not so much about ideology as lack of understanding of the true face of space, time, and knowledge. Similarities of description can be found in concepts ranging from the simplest principle of meditation to the possibilities of mathematical equations for karma. Notions of emptiness from the 2nd century Buddhist philosopher Nagarjuna's teaching have much in common with the antimatter of universal fluctuation. In The Path to the Middle, Kensur Yeshut Thupten says, scientists today understand dependent arising. Well, they can identify what comes from which causes. Their expertise, however, lies with the temporary